Hello students, this is Narendra Kumar Devedi, once again welcoming you all in the next lecture of Electrostatics class 12th. So our today's first topic is electric field lines. Electric field lines, in short, to define it, definition for the electric field lines, we can say electric field lines are basically an imaginary straight or curved lines which represent the presence of electric field and which shows the prevalence of positive charge if at all it is allowed to move. तो इलेक्ट्रिक फील्ड लाइंस ऑफ फोर्स बेसिकली वो इमेजिनरी स्ट्रेट लाइंस या कर्व्ड लाइंस होती है जो कि किसी भी पॉजिटिव टेस्ट चार्ज के मूव करने की डायरेक्शन को या मूव करने के पाथ को रिप्रेजेंट कर रही होती हैं. सो नाउ वी मूव ऑन फॉर प्रॉपर्टीज ऑफ electric field lines. So under this we can say for the first property that these electric field lines are discontinuous. It means they start from positive charge and are supposed to terminate at negative charge. So for the first property, what can we write? These lines are discontinuous. So this is our first property of electric field line. Now here if we have positive charge, so they are directed away from this positive charge like this. And if we have a negative charge, so they are directed towards the negative charge like this. So this is the first property representing discontinuation of these charges, these lines. Now for the second property, what can we say? These lines never cross each other. Two electric field lines will never cut each other at all. So here we can write two field lines do not cut each other. What if we assume that two field lines cut each other at certain point? क्या होगा अगर हम ये माने कि दो इलेक्ट्रिक फील्ड लाइंस एक दूसरे को कट कर रही होती हैं किसी भी पॉइंट पे? Now let's see, suppose these are two lines. This is first line and this is second line, and we are assuming that these two lines cut each other. This is first line, this one is second line. Now they are supposed to cut each other at this P point. Now there's another property of electric field line, that if we draw a tangent at any point on the field line, so that tangent will represent the direction of electric field line at that point. तो हम उस प्रॉपर्टी को अगर यूज करें और इस पॉइंट पे इस फर्स्ट लाइन के ऊपर एक टेंजेंट ड्रॉ करें, just to have the direction of electric field at this point. So this is going to be along this. So let me represent it by E1. Now on this second field line at this point only, if we draw again a next tangent on second line at point P, just to have the direction of electric field at this P point of second field line. So this is along this. So this condition is actually impossible. एक सिंगल पॉइंट पे कोई भी इलेक्ट्रिक फील्ड दो डायरेक्शन पजेस नहीं करेगा. इट इज इम्पॉसिबल. और इस कंडीशन की वजह से ही हम ये बोलते हैं कि दो फील्ड लाइंस कभी भी एक दूसरे को क्रॉस नहीं करेंगी. सो लेट्स हैव नेक्स्ट थर्ड प्रॉपर्टी. सो फॉर द थर्ड प्रॉपर्टी वी कैन से that lines of force start from positive and end on negative charge. अगर हमारे पास में दो चार्जेस हैं, थर्ड प्रॉपर्टी, these lines start from positive charge and end on negative charge. So this is our next property. तो हम अगर दो चार्जेस की यहां पे असेंबली ले लें, सपोज दिस इज आवर पॉजिटिव चार्ज एंड दिस इज आवर नेगेटिव चार्ज. अब ये दो चार्जेस में अगर हम इलेक्ट्रिक फील्ड लाइन शो करें तो इलेक्ट्रिक फील्ड लाइन क्या होगा, इधर से ओरिजिनेट होगा और इसकी तरफ टर्मिनेट होगा. पॉजिटिव चार्ज से ओरिजिनेट होके इट एंड्स ऑन नेगेटिव चार्ज. सो दिस वे दीज लाइंस विल बी डायरेक्टेड लाइक दिस. सो दिस इज द प्रॉपर्टी. नाउ फॉर द फोर्थ प्रॉपर्टी वी कैन से these possess longitudinal tension. Lengthwise these, or you can say they possess longitudinal tension. तो ये जो longitudinal tension है, lengthwise जो tension है, वो क्या represent कर रहा होगा, that the force of attraction between the unlike charges. So this longitudinal tension, lengthwise tension represents the, you can just even write here, they possess longitudinal tension representing attractive force between unlike charges. So this is our next property. Lengthwise they experience tension and that tension shows the force of attraction between unlike charges. Now for the fifth property we can say they exert lateral, means perpendicular to the line, lateral pressure on one another. Now this lateral pressure will represent what? Lateral pressure shows it is the force of repulsion between the like charges. So here you can write representing the repulsive force between two like charges. So this is fifth property. Lengthwise, as we said for the fourth property, they experience a tension lengthwise, longitudinal, representing attractive force between unlike charges, and perpendicular to the length, laterally they exert pressure on one another, representing the force of repulsion between two like charges. Now for the next property, we can say number 6, we can say they do not pass, we can say, instead of saying form, pass through a closed conductor, What does this mean? We can say that is the charges, that is we can say no lines of force exist within the conductor. So inside the surface of the conductor, there will not be any kind of presence of electric field lines. They are out of the surface, but inside the surface of the conductor, their existence is no more seen. So this is our sixth property. Now for the last property, we can say the relative density of electric field lines represent the strength of electric field at that region or at that space. So here we can say for the next property, that was perhaps number 7. Earlier it was 6th number. So the relative density, we can say the relative density of field lines indicates the strength of electric field. So how dense the field lines are at certain region of space. So those denseness of electric field lines will represent the strength of the electric field at that particular point of the region of space. So this is the meaning of this property. So with this, this topic ends here. Let's have next topic, and the next topic would be electric dipole. So let's have second topic now today. So here we can say electric dipole is our next topic. So to define it, what can we say? An assembly of two unlike point charges placed very close to each other form electric dipole. So what can we write here for the definition? So it is a pair of equal and opposite equal and opposite point charges placed, or you can say separated by a very small distance form electric dipole. So this is the definition. Now for examples, as we have like in chemistry you might have studied H2O, NH3. So these are few examples of naturally existing electric dipole. NH3, etc. So these are few examples. Now we can see actually these that means suppose this is positive charge plus Q and this is negative charge minus Q. Magnitude wise they both will be equal, and the separation between them is being taken here 2a. So this is the separation between these two charges. So this assembly, this pair is an electric dipole. So these are basically cylindrically symmetric. So we can say the electric field produced by electric dipole is cylindrically symmetric. So the electric field that this dipole will form at certain point along its length, so that is cylindrically symmetric. Okay, means if we draw an imaginary cylinder around that dipole, so that at every point on the surface of that cylinder, the strength of electric field is going to be uniform, constant. That's the meaning of that electric field being cylindrically symmetric. Now, what can we say for the important point as next? The strength of dipole is a vector quantity called, what do we say, this vector quantity of which represents the strength of dipole? It is called the dipole moment. So this is the vector quantity, dipole moment. So electric dipole moment, actually let's define that also. Electric dipole moment, what can we say for that? Electric dipole moment is basically the product of magnitude of either of those two charges with the separation between them. So that gives the electric dipole moment. So electric dipole moment is symbolically represented by small vector p, and it is the product of magnitude of either charge with the separation between those two charges. Now it's a vector quantity, so let me make it a vector by multiplying a unit vector p cap taken along this vector P. So this is the dipole moment. For magnitude, what can we write? We can say it's Q into 2A simply. So its SI unit will be, and its direction, directed from negative to positive charge. We can write it for the direction of this, whose magnitude is Q into 2A. So this is for SI unit. What can we say? SI unit of dipole moment will be Coulomb meter. So this is Coulomb meter. Now dimensional formula also you can just work out. Dimensional formula. So dimensional formula, Coulomb has got ampere into time, AT, and meter is length. So we can write its dimensional formula to be M0 L1 T1 A1. So this is the dimensional formula of this dipole moment. Now let's have the next topic is electric field produced by this dipole at a point situated on the axis of the dipole. So let's have the next topic with us now. Electric field produced by an electric dipole at a point on its axis. Electric field due to electric dipole at a point on the axial position. On the axial position, this is actually also known by another name, that's end-on position. End-on position. Okay, to begin with, let me just draw the diagram first so that we can have a brief idea of the proceeding. Suppose this is negative charge which we are taking at point A, and here we have similar opposite charge plus Q at point B. Now these two are forming the dipole with separation 2A, and suppose this is the midpoint of them. So this length will be A and this will be A, half of the dipole length. Now on the axial position of it, from certain distance from the mid of this dipole, we are assuming a test point, and that test point that we are taking now is say P, and its distance right from the mid of the dipole is being taken to be small r. Now at this test point, we'll be representing the direction of electric field taking the presence of positive charge here as source charge, and next electric field direction will be shown taking this negative presence of source charge. So here, due to this charge, electric field will be directed away from this. So here I am just representing it by vector E2. Now due to this negative charge, the electric field will be directed towards this point B. So this is I am representing by vector E1. Now the resultant electric field will be along this E2, vector E, as this E2 will be more in comparison to this E1. For that reason, we'll be taking the resultant along the higher magnitude electric field. So let's begin with, now we say the electric field produced by minus Q charge at P is vector E1, which is equals to 1 upon 4 pi epsilon naught. Suppose these charges are present in a medium which is having the dielectric constant as K. So for that reason I am just writing here K in multiple to this epsilon naught K into source charge, that's magnitude of source charge, Q upon distance square. Now what is the distance of this negative source charge from this point P? It is A plus this R. So we write now R plus A square. Now to make it a vector, we must have a direction. And for that direction, we are multiplying the right hand side by a unit vector. So the unit vector along this E1 will be minus of I cap, as this E1 is along negative x-axis. For that reason, minus I cap. Similarly, we can write electric field produced by this positive charge at point P. So vector E2 will be equals to 1 upon 4 pi epsilon naught K source charge upon. Now what's the distance of this from this? It is R minus this A. So we write now R minus A square. And what's the direction of this field produced by positive charge at P? It is along plus x-axis. For that reason, we are multiplying it by positive I cap. Now, using the principle of superposition, we can write the resultant electric field at P. So, using principle of superposition, vector E resultant electric field will be the vector sum of electric fields produced by two different charges at that point. Now here we can say, since mod of E2 vector is more than mod of E1. Now see, what decides which one will be greater? As charges are of same magnitude, so this is a constant quantity, only this distance will decide which electric field will be more and which else will be less. So as can be seen, this distance is shorter than this one, so hence it is inversely proportional. So shorter distance will produce strong electric field at this P point. For that reason, we are saying mod of E2 is greater than mod of E1. So the resultant electric field will be taken along this E2 direction. So here now we write for resultant electric field. So for resultant electric field, we can say that E equals to, now see this Q upon 4 pi epsilon naught K, this will be a common term, so we can write it separately. So it is Q upon 4 pi epsilon naught K. Now inside we have E2. E2 is this one. So this is 1 upon R minus A square minus this one 1 upon R plus A square. 1 upon R plus A square, and to make it a vector, if we just take magnitude, so it will be quite okay. Now if you just want to make it a vector, so you should multiply it by I cap. So that means along positive x-axis this resultant field is being taken. Now let's simplify this. Q upon 4 pi epsilon naught k into, have the LCM first now. So it will be this into this. So r minus a square into r plus a square. Now this comes here, r plus a square minus this r minus a square times this I cap. Now there we can just write for next step as here, let me make some space so that we continue thereafter. Now here we can say, for the simplification, vector E equal to Q upon 4 pi epsilon naught k times, here at denominator we can write a square minus b square and its whole square. So here we can use property a square minus b square. So that will be r plus a plus r minus a plus b into a minus b minus r plus a into this I cap. So here a and a will get cancelled, and here r and r. So this 2r and this 2a will make, here we can write 1 upon 4 pi epsilon naught k into this q into this 2r. Instead of this 2r we write 2a into this 2r upon, this is r square minus a square whole square into I cap. Now try to identify this term q into 2a. This is dipole moment. So we can write further 1 upon 4 pi epsilon naught k p into 2r upon r square minus a square whole square I cap. Now for the special case, we can say special case, if say the test point is taken at very far off distance, then the r will be much more greater than half length of dipole. Under that special case we can neglect this a square because it will be quite smaller than this r square. So just taking that into account, we write 1 upon 4 pi epsilon naught k into this p vector we can write now into 2 upon this r square, and its square will cancel this r, leaving only 3 r cube here. So this is the last outcome. Let's have the last topic of today, and that will be the electric field due to the electric dipole at a point on the broadside or on the equatorial position of the dipole. So that's the last topic of today. Let me just make the space. So the next topic of today, at a point on the equatorial position. So this is called broadside on position. Broadside on position. So this is our next topic. Okay, so let's draw the diagram first. Suppose this is our dipole getting formed by two opposite charges. Point A minus Q charge is supposed to be present, point B plus Q charge is supposed to be present, and this is the midpoint of the dipole. Half of length of dipole, another half A. Now from this perpendicular bisector position of this dipole, we are assuming the presence of positive discharge P, and now say the electric field produced by this positive charge at this point P will be directed away from it, and this is we are having vector E2. Now this electric field being produced by this negative charge at this point P will be along this, and this we are representing vector E1. Let this angle be theta, so this has also to be theta. Now taking this as the resultant field, as per the vector sum rule, we can just represent this to be electric field, resultant electric field E. Now there are two methods. First, we are just having the resolution of these two electric field components at this point. So with this E1, this angle will be theta and this also will be theta. So when we resolve it, so the component of this is E1 cos theta along this, and when vertical will be downward, and when this E2 is resolved, the horizontal will be along this, so this will be E2 cos theta, and vertical will be opposite to that of vertical component of this E1. So let's begin with, now we write the electric field produced by minus Q charge at P is vector E1, which is equals to 1 upon 4 pi epsilon naught. Better would be if we just write magnitude only. Direction will be written just in a bracket. So E1 will be 1 upon 4 pi epsilon naught K, charge magnitude upon distance. Now what's the distance? Taking this right angle triangle, this is the hypotenuse, so this is this distance we are taking R. So under root R square plus A square. So here we write R square plus A square, and similarly the electric field produced by this positive charge at point P, that's E2, we can write 1 upon 4 pi epsilon naught K Q upon, again this distance square, BP. So BP would also be under root R square plus A square, and when we have the square of that, R square plus A square, the root will get cancelled. Now clearly we can say, this E1 is just equal to E2. With this, हम अगर इस पॉइंट P को देखें तो पॉइंट P पे जो वर्टिकल कंपोनेंट होगा E1 का वो डाउनवर्ड होगा और E2 का अपवर्ड होगा, और ये मैग्नीट्यूड वाइज दोनों इक्वल हैं, इस वजह से वो दोनों कैंसिल आउट कर रहे होंगे बिकॉज ऑपोजिट इन डायरेक्शन, और हमारा ये जो हॉरिजॉन्टल कंपोनेंट दोनों E1 E2 का है वो सेम डायरेक्शन पे होने की वजह से एड अप हो जाएगा. सो द टोटल और नेट इलेक्ट्रिक फील्ड at P we can write E equal to E1 cos theta plus E2 cos theta. अब हमारा E1 E2 दोनों इक्वल है, तो हम इसको लिख सकते हैं 2E1 cos theta. तो हम यहां पे वैल्यूज अगर रखें, So therefore E हमारे पास आ जाएगा 1 upon और 4 पाई एप्सिलॉन नॉट के कांस्टेंट होगा, और ये हमने लिखा 2 ये वाला, और E1 में Q है, सो Q अपॉन R स्क्वेयर प्लस A स्क्वेयर इनटू कॉस थीटा। अब हम कॉस थीटा अगर यहां से वर्कआउट करें राइट एंगल ट्राइंगल लेके, सो बेस अपॉन हाइपोटेनस, तो हमें मिलेगा A अपॉन R स्क्वेयर प्लस A स्क्वेयर होल रूट। अब ये 2QA आइडेंटिफाई है, इट इज डायपोल मोमेंट 1 upon 4 pi epsilon naught k, it will be P upon R square plus A square 1 plus half, that's 3 by 2. अब अगर हम स्पेशल केस ले लें, स्पेशल केस, तो स्पेशल केस में हम क्या बोल सकते हैं कि अगर हमारा टेस्ट पॉइंट फार ऑफ पोजीशन पे हुआ तो ये जो R होगा वो हाफ ऑफ डायपोल लेंथ से ज्यादा बड़ा हो जाएगा। अंडर दिस स्पेशल केस वी कैन निग्लेक्ट दिस A स्क्वायर बिकॉज इट विल बी क्वाइट स्मॉलर देन R स्क्वायर। सो वी हैव E टू बी इक्वल टू 1 अपॉन 4 पाई एप्सिलॉन नॉट K P अपॉन R स्क्वायर, getting cancelled with this 2, leaving R cube here. Now for the second way, if you don't wish to just resolve E1 and E2 into their components, so you can use that parallelogram law of vectors addition. So parallelogram, under that condition, parallelogram law of vectors addition, if we use for second way, E will be E1 square plus E2 square plus 2E1 E2 into cos of angle between them. तो उन दोनों के बीच का एंगल है cos 2 theta under root. You just proceed using this by placing those E1 and E2 and finding out cos 2 theta. Thereby you'll reach at the same conclusion this one, and you just continue taking this special case and finally come to this. Now we can have comparison between axial electric field intensity of dipole and broadside on, that's equatorial electric field of dipole. So since E axial we had equal to 1 upon 4 pi epsilon naught K into 2p upon R cube it was, and this is E equatorial, so this is just the double of E equatorial, so we can write E axial equal to 2 times of E equatorial. So with this we end up today's lecture. So students, do like and subscribe my channel.